Everyone, it's me, Billy Younger again. This time I'm working a problem using Ampere's law, which sort of requires you to have a little bit of intuition about how a magnetic field forms based on a certain amount of experience with currents. So, specifically, if you've already studied the law of B of Savart, you have some sense of how the right-hand rule plays a role in the direction and stuff like that. And with that and basic symmetry principles, you can make a hypothesis about the form of the magnetic field and then use Ampere's law in a truly weird way to solve for the integrand on the left-hand side of Ampere's law. This is an example where I'm going to apply Ampere's law to an infinitely long straight wire carrying a current I upward, and I'm going to calculate the electric field, or excuse me, the magnetic field a distance r away from it. So let me begin by sharing my iPad screen. So here's a drawing showing the current carrying wire. The current carrying wire is represented by the two blue lines, one being the left edge, the other one being the right edge. Also, the current going through it is drawn by that little itty bitty, or indicated by that little itty bitty red vector that you see on the positive z-axis. Notice I do have the x-axis pointing out of the page, the y-axis being parallel to the page and to the right, and again, I'm actually referring to the positive x-axis and the positive y-axis, and the positive z-axis, of course, being pointing upward. This orientation of my x, y, z axis with the wire basically centered on the z-axis allows me the use of some very common uh, unit vectors to specify the direction. So that's why I've chosen to do it this way. And now I'm going to go ahead and explain to you guys how to use Ampere's law and how to solve this problem. So solution. So what we're supposed to use is Ampere's law, and Ampere's law says the closed integral of B dot dl is equal to mu zero times I enclosed. And uh, just like Gauss's law when we did that one for the magnetic field, or I mean for the electric field, in this case we have a type of expression to represent what I is, and in this case we actually normally use I is equal to the integral of j dot dA, where J is the current density. And this is often the case, but usually we don't have to use the I equals the integral of J dot dA to compute I. It's normally just a simple calculation of what I is, or in some cases just looking at the diagram. But the main thing here is this integral, Ampere's law, is on the integral is a line or surface integral, and it's actually over a closed line. I said a line or surface integral. I meant a path or line integral, not a surface integral. And it actually is over a closed path. That's why the circle's on the integral. And that circle also, of course, appeared in Gauss's law, but that one was a surface integral. This one is a contour or path or line integral. So I wanted to give you an idea of how we're going to go about using that, but the trick to using Ampere's law is one, if you're going to use Ampere's law the way I'm teaching you right now, that means you're planning on using the closed integral of B dot dl equals mu zero I to compute what B, the magnetic field, is. But in order to do that, you have to make a general hypothesis of what the magnetic field depends on in terms of its strength and what direction it acts, because the only way you can compute the left-hand side is by finding a magnetic field function that, when dotted with dl, which is part of the line segment on the path that you go in a complete circle on, is only easy to compute when the magnetic field is parallel to that dl and therefore constant on it, or it's completely perpendicular and therefore the left hand side becomes zero. So you've got to actually pick out the symmetries for which that works. One of which, of course, is a cylindrical symmetry, like an infinitely long wire or a coaxial cable. Another symmetry that we can use is a symmetry associated with a solenoid, which you can imagine a solenoid is like the grade school electromagnet you might have made when you said basically took a nail and wrapped wire around it. Because when you wrap the wire around the iron nail, that is the actual shape of a solenoid, is that wrapped iron wire, excuse me, that wrapped wire in a neat coil. That's the solenoid. Another one is if you imagine a really long solenoid and you bend it from a straight long thing into a donut where the two ends came together, that would be a toroid, and that's the other symmetry that we can use to solve for B in the anagram of Ampere's law. So that's an explanation that might sound reasonable or it might sound completely scary. The main thing is it doesn't make any sense until you actually apply it. So hopefully, me showing you this will help. So first off, what I got to do is I've got to remember that when I learned the law of Biot-Savart, which said that mu 0 I over 4 pi times dl cross rp minus r dl over rp minus rdl magnitude cubed, that is basically the law of Biot-Savart, and that allows us to figure out the direction by taking the cross product of the dl vector, which is a little length of line segment along the current carrying wire that happens to point in the direction of the current, and then a cross product of that with rp minus rdl, and rp minus rdl is basically the vector that connects the point at which you wish to know the magnetic field to the actual DL that you're using. So when you actually compute those two vectors and then take a cross product, that gives you a direction. So in this case, we could imagine a DL would actually be along the z-axis, and we need to cross that with RP minus RDL. What we're looking for here, though, is a distance r away on the y-axis, say. In actuality, by the symmetry of this, we can rotate this about the z-axis at any angle and then redraw our x and y axes, and it'll always be the same. And because of that, we can sort of say that at least when the r is along the y-axis, uh, we're going to have a very specific RP and a very specific RDL and a very specific DL. So in this case, what we would imagine with actual the law of Biot-Savart is that DL would essentially be like that vector I or that arrow that you see representing the current I. So it actually being an arrow looks just like a vector. So you could actually imagine this as your DL vector, even though it's just supposed to represent that the current I is traveling upwards along the z-axis. But if you treated that as your DL vector, and then your RP minus RDL would actually be a vector that sort of points from here to here. Actually, I could draw that a little neater. So this vector right here, let's see if I can, I'm trying to highlight this. I guess it's just going to erase all that. Okay, so I'll draw it again. So that represents the vector r p minus r dl. So if you imagine taking a cross product of I hat, which is, excuse me, of the dl, which is in the k hat direction, that's that way, and you take a cross product of that with the rp minus rdl, which points down and to the right. So you see my index finger, my middle finger is pointing sort of parallel to the blue rp minus rdl vector, and then the only way we can do that is when my hand is oriented, my right hand is oriented this way, and I see that my thumb is therefore pointing into the page. So the actual DL, or excuse me, the actual B vector, the magnetic field vector for this particular coordinate, or for this particular figure, actually just points into the page along the y, when the point is along the y-axis. So we could basically say, I'll mark this with a red line, and I'm trying to draw it parallel to the x-axis. So this is about the direction of the magnetic field when we're talking about that particular point right here where I just drew the red dot and wrote P like that. So if that's our point, we can see that the magnetic field is actually lying in the plane, the XY plane, but points parallel to the negative x-axis. Similarly, if we imagine the same point, a distance r away, but imagine it at basically along the negative the negative x-axis, excuse me, then it would be right here, and then you drew the RDL, or excuse me, RP minus RDL, and it would be again from the bottom of that little red vector on the z-axis to that red dot right there. And when you cross those two, you're going to see that in this case, the magnetic field is going to point to the left. And then, of course, if you look over here and imagine that the R was, let's say, way over here, then RP minus RDL would be this vector. And when you cross them again, it's RP minus RDL. This time it's pointing out of the page, which I have to represent as parallel to the x-axis basically, and that would be basically it. And then finally, if we considered it pointing along the x-axis right here, then RP minus RDL would point to the right, and we would get that our vector would be essentially this. So that's what the vector magnetic field direction is for each of those points, as if each of those points is a distance r away. So I'd put r there, I'd put r there, and I'd also put R right here. So that is an actual picture of the magnetic field at various locations. Now, additionally, another way of making this look a little even more clear is by drawing a plane perpendicular to the actual current carrying wire. And that plane, I would say, would be basically, no, that's not a good, yeah, that's a good one. Basically here to here. That part didn't work out so good. So right about there. And then I'm going to go back here. And I'm going to go back here. And this is a plane that should be perpendicular. Actually, I got it a little messed up. This one, this point right here is, ooh, let's undo that. I don't know what just happened, but it was not what was supposed to happen. Okay, I lost my x-axis somehow, but that is weird. Never had that happen before. But anyways, let's just draw another x-axis because I have no idea how that happened, but we saw it happen, and that'd be, what we have to do. Yep. That still did not work. Hold on, let's try again. So now we have our x-axis back. Now, the mistake I actually made, as I was saying, was in my drawing of the two-dimensional plane here. I didn't quite draw it like I was supposed to. So what it's supposed to be, I was trying to represent it as two squares to the left of the black line, two squares to the right of the black line, which is the x-axis, but that did not necessarily work out the way it was supposed to. So let me erase some of this, make this a little more clear. I think this one will actually work out okay if I left these lines, but just in case, I'm going to go ahead and get rid of them. Now I'm going to take my black pen, mark my R back here. I'm going to recognize that the plane being two squares to the left of the positive x-axis at this particular location means it extends all the way to here. And for to the right of the x-axis would be, there's one square, here's the other square. Then back here I need to the right by 2. That would be right there. And to the left by 2, which would be right here. And of course I drew it stopping at the wire, and that's because the wire is actually in front of it in space. And now I'm going to do it again over here, and now we have the plane that I was actually trying to draw all this time. So there's the actual plane, and if we try to trace exactly what I'm talking about in terms of the magnetic field direction here, what we can do is I can draw an oval, which I'm going to take to be about 3/4 of a circle here, 3/4 of a square here, and I'm going to say it is about 3/4 of a square down this way as well, maybe a little bit more because it's closer to us. And then I'm going to say this is going to be right there. and this is going to be right there. So now I can draw an oval as follows. Actually, I can't draw an oval this way, so I'm going to try to draw it by hand. So what I've drawn here is a red line that represents a circle whose center is the center of the wire and whose radius is r, the distance it is away, of course. So you can say this distance right here would be, let's say, a capital R or something like that. But the main thing is because it's a set distance, that means the magnetic field strength is the same on all of them because we think that the magnetic field strength should only depend on the distance R perpendicularly from the wire. So with that in mind, now I'm going to draw exactly what the magnetic field direction is. This time I'm going to draw it in a color purple just so it'll stand out a little bit better. Oops, that did not work. So switching again to purple, if I can ever get this to open. So what we see is the direction of the magnetic field at this front point, which is between us and the wire, is to the right. And then to the right of the wire, the magnetic field would be basically into the board or into the screen or into the page. And then if it was back behind the wire, it would be to the left. And then if it was to the left of the wire, it would be out of the page, out of the board, or out of the plane of the drawing, that is. So that's ultimately what the magnetic field direction is. Now that we've used sort of the principle of the Biot-Savart law and how you calculate the actual direction, we can see that it is consistent with the right-hand rule I've been teaching you, which is basically if your wire is going up and down, and let's say the point is pointing up, that means the current is going in the upward direction. So if take your right hand and lay your right thumb in the direction of that current, you curl your fingers around the wire, and then you can look as you're doing now from above as if the current is headed right towards your forehead, and you see that the fingers curl around the wire in a counterclockwise direction. That's what I'm showing with that round circle. There's the counterclockwise direction at each point on that circle, which looks like an oval from this perspective, but it's a circle. But each point on that circle, we would expect the magnetic field to be tangential to the circle at that point. That's how we figure it out. That's how I know that, for instance, the magnetic field to the right of this wire is in the board. The magnetic field behind this wire is to the left. The magnetic field to the left of the wire is out of the board. And the magnetic field between us and the wire, in other words, in front of the wire, is to the right. So now that I have that, I'm going to go ahead and make a hypothesis about the magnetic field. My hypothesis is this. Now, all of this was me sort of, I don't want to call it just navel gazing, but it sort of was that. It was me trying to express to you exactly how I'm using the law of Biot-Savart and then very shortly the right-hand rule to work out the directions of the magnetic field associated with a wire, infinitely long straight wire carrying a current upward. So I went through all of that specifically so you'd understand my thinking, and we shouldn't go through all of that every time. It's just a matter of me trying to express exactly what I was thinking. So my hypothesis now is that the magnetic field B will be some magnitude that only depends on r, the perpendicular distance from the wire to the point in question, and then it's going to be in this very specific direction that these purple vectors represent, which I am going to call the theta hat direction because I think you can see that it is, in some sense, exactly the direction that theta would increase for each of those particular theta values. So for instance, when theta equals 0, if you remember polar coordinates, theta equals 0 means that you're actually on the positive x-axis. So you can see that this point right here corresponds to theta equals 0. And if I wanted to take a line that's along the x-axis at theta equals 0 degrees, and I wanted to increase the angle theta, it would move from this line to, say, this line. And you see that clearly that was the direction that theta increased. If you move over to just a little bit, then theta is going to be that way. If you move just a little bit more, theta is going to be that way. But in every case, what you're discovering is that it's a line that's perpendicular to a radial line. And that is the vector that I'll call theta hat. And I'm going to, even though I've shown you theta hat several times in these examples and other examples on my YouTube channel, I'm going to show you exactly what theta is. And now you can think about it and see that, in fact, theta hat acts just like the direction of those little purple vectors. So theta hat, I'm going to tell you, is actually equal to the negative of the sine of theta times the I hat direction plus the cosine of theta times the j hat direction. And perpendicular to that is the r hat vector, which normally we would put that first. It's sort of like x, y, z. You should go r theta z if you're talking about cylindrical coordinates, or r theta if you're talking about just polar coordinates. So the r hat vector, just to give it to you, is cosine theta I hat plus sine theta j hat. And I think you can look at this and realize that dr hat over d theta is actually going to be, remember, the I hat, j hat, and k hat are special constant vectors, so that when you take a derivative or an integral of them, you can just pull the I hat, j hat, or k hat right out in front of the derivative or the integral, because they're constant and they don't have to be differentiated. So in this case, I'm doing dr d theta, and of course the derivative of cosine theta is negative sine theta, and the derivative of sine theta is positive cosine theta. So you see that dr d theta actually gives me theta hat. So now, looking at theta equals 0 in this particular expression here, if theta equals 0, you get the sine of 0 is 0, so it's not going to have any x component, but you get the cosine of 0 is equal to 1, so the whole vector is going to be pointing in the positive z direction when theta, or excuse me, the positive y direction when theta equals 0 degrees. That's exactly what we get here. Now, if we want to go to theta equals 90 degrees, we believe, as this vector or this vector shows, just like this vector or this vector showed before. Now we're at theta equals 90 degrees, and if you take the negative sine of 90 degrees, the sine of 90 we know is 1, so the sine of negative 90 should be, or the negative of sine of 90 should be negative. So we'd see this is, or excuse me, negative 1. So we see this is negative 1, and then the cosine of 90 is actually 0. So we expect this to just point in the negative x direction, which is exactly that direction that we have drawn here and here. If you try theta equals 180 degrees, that would mean theta would be back here. And of course, the theta being 180 degrees, the negative of the sine of theta when theta is equal to 180 is 0, so it's not going to have any I hat component. But the cosine of 180 degrees, in this case, we can see the cosine is negative 1, so we're going to get pointing in the negative y direction, which is also the same direction that these two vectors point. So I think with those three tests, you probably are confident that I am correct about calling theta hat negative sine theta I hat plus cosine theta j hat, and more specifically saying the magnetic field strength is only a function of the r, the horizontal or the perpendicular distance from the wire to the point P, and that it points in the theta hat direction. Now that we have that, I'm going to treat that red curve that we drew right there, we're going to treat that as if it is the contour along which we're going to integrate. So use this path or contour as the curve along which the line integral is computed. So the left-hand side of Ampere's law is a closed integral of B dot dl. That means we're going to integrate over a closed path, and specifically this closed path is going to be indicated as a counterclockwise integration around this red circle that I've drawn on this green plane. So that red circle is called an Amperian loop. Our Amperian loop. So that is what we're going to integrate along. And there is a right-hand rule associated with Ampere's law. Specifically, if you take your right hand and you curl your fingers around the direction of the contour or the path that you're going to follow in the integration, if you do that, then your right thumb points in the direction of a positive current. And if you find that the magnetic field, or excuse me, the current is going the opposite way, then that current is going to be a negative current. So we have to link the right hand side and the left hand side together by recognizing that sign convention. But once we have that, we're good to go. So now I'm ready to actually apply Ampere's law. So the way we do it is like I did with Gauss's law. Specifically, I attack the left hand side, work out what it is. And by the way, with Ampere's law, the left hand side is always supposed to be basically some magnetic field B times some length of a path or length of a straight line or something like that. There might be some plus zero terms and stuff like that, but the main thing is it's always going to be the left hand side turns out to be some magnetic field strength B, which in our case might be B of R, times some length of a path like L. Okay, so just keep that in mind. That's what the left hand side is. If you ever have to physically do an integral on the left hand side, you've done something horribly wrong if you're trying to solve for B. So now that we have that, I'm going to go ahead and write out the left hand side. So the left hand side of Ampere's law says the closed integral of B dot dl, which equals the integral over that contour I just told you, but now I'm going to plug in B of R. Remember that means B a function of R, not B times R, and it's supposed to be in the theta hat direction. And then similarly, as we'd worked before, the DL will be a little segment along an arc. And I think you probably remember that that little segment along the arc from S equals R times theta should be DL equals R d theta. So I'm going to go ahead and say R d theta, where R is the radius of that little circle in there. And I'm actually using the little r, even though I wrote a big R there. I could actually imagine this circle being at the specific locations R that I listed here, even though I didn't actually draw it. But that's what we're going to use. We're going to pretend like this is actually just lowercase r, just so we can have it come out in terms of the answer, lowercase r, which is what we were supposed to work anyways. So again, this is going to be r d theta for the length of the line segment, and I think you'll convince yourself that the direction is in fact also theta hat. And the beauty of this is that the dot product is what we call a linear operator. That means I can pull all the constant parts out in front. So B of R times d theta can all come out in front of the dot product. And then I'll just take the dot product as the dot product of the two remaining vectors in the same order that they were. And in this case, theta hat dot theta hat is going to be 1 times 1 times, in this case, the cosine of 0 degrees. because the formula for the magnitude of a dot product is A dot B is equal to the magnitude of A times the magnitude of B times the cosine of the angle between them. In this case, the two vectors are exactly unit vectors, so A and B are both 1, and the vectors are actually identical, so they're actually parallel, and therefore the angle theta is 0 degrees. So that's how we're getting B of R d theta times theta hat dot theta hat, where the theta hat just becomes 1. In fact, I can write it right there and just say this is 1. So now that we have that, we also realize that since we are integrating along a path of radius r, then b of r and r itself are both constants and therefore can be pulled out in front. So I'm going to say b of r times the integral d theta from theta equals 0 to 2 pi, and finally we get just 2 pi r b of r for the left-hand side. Notice that is a length. In this case, it happened to be 2 pi r, which is the circumference of the circle, times a b of r. So it is a length times b of r, as I advertised. Your left-hand side of Ampere's law, if you're solving it for the integrand b, is always supposed to work out to just be some length times the magnetic field. Again, there might be other terms that are 0, or there might be multiple terms that are like 2 pi r times b, or b times l, or something like that. Now we're going to do the right-hand side, and actually, as long as you're not doing weird things like trying to compute the magnetic field within the wire itself, then the right-hand side is really, really trivial. Otherwise, it could be bad because you might have to use the integral form. So now I'm going to write down right-hand side, and that's the right-hand side, just like that was the left-hand side. And the right-hand side is mu 0 times I enclosed. If you take your right hand and curl your fingers around the direction of the red path that we're integrating along, you'll see that your right thumb is pointing upward, which is parallel to the current. So the current that actually goes through or is enclosed within that loop is a current in the upward direction, which is a positive current, and therefore the right hand side is just going to become mu 0 times I, because that's the only current that's there. Okay, now all we have to do is set the left hand side equal to the right hand side and then solve for B. And then we'll express it back in terms of our hypothesis, where b, the vector, is equal to the magnitude of b of r, or the magnitude, which we call b of r, times theta hat. So right-hand side equals left-hand side, or left-hand side equals right-hand side, is mu 0 I is equal to, sorry, I wrote left-hand side first. Actually, I should have wrote it the other way. Sorry. So I'm going to say 2 pi r times b of r is equal to mu 0 times I, and therefore you can go ahead and solve for b of r, and you'll get b of r is equal to mu 0 I over 2 pi r. And using our hypothesis, that tells us that b, the magnetic field, is going to be b of r times theta hat, which is equal to mu 0 I over 2 pi r theta hat, which is exactly the hypothesized direction, which of course we just made that, and we got the magnitude that we had already been given as if it were experimental data from your textbook. When they just opened up chapter 27, I think it was, they just said there's a magnetic field that exists as a result of a current. That magnetic field is mu 0 I over 2 pi r. We have the magnitude now, and we've used our understanding of the law of Biot Savart to figure out the direction, and hopefully that'll help. Hopefully you now have some sense of exactly what the Ampere's law is and how it can be used in this weird way, not unlike the weird way we use Gauss's law to extract the integrand from the left-hand side of the equation. So that's about it. Thank you for stopping by. Have a good day.